Hey guys, this is Miss Peters, and today I'm going to go over your worksheet that you were just given called the heating curve of water. This is exactly how I'm explaining this worksheet to my class. So you should have on your worksheet something at the top that looks like this little table. I want you to add the labels enthalpy of fusion and enthalpy of vaporization underneath these flat lines. And we'll talk more later about what that means. And then also, this is a heating curve of water. So what that means is this shows the different states of matter that water will be in at certain temperatures. So if you weren't aware, water or ice, solid ice, melts at 0 degrees Celsius. So we're going to label this right here 0 degrees Celsius, and then liquid water boils at 100 degrees Celsius. So we'll label that there. And so this first, and I'll highlight it in green, diagonal line represents when water is a solid. So at less than 0 degrees Celsius, water is in the solid state of matter. And then this flat line is when fusion is occurring. Fusion is another word for melting. And then once ice has melted, it's now liquid water. And so this second diagonal line represents when it is you can't read that, liquid. So between 0 and 100 degrees Celsius, water's in the liquid state of matter. And then if you've ever boiled water before, it doesn't happen automatically and go from a liquid to a gas. It takes a little bit of time once it gets to 100 degrees Celsius. And so this second flat line, vaporization, is where the boiling is occurring. That flat line is where the boiling is occurring. And then once water gets above 100 degrees Celsius, so there and up, it is in the gaseous state. So I said I had water at 45 degrees Celsius. You should know based off this heating curve, it's a liquid. If it was negative 45 degrees Celsius, that's below 0, it would be over here and it would be a solid. And something important that you should note on this heating graph or this heating curve is that this x-axis shows how heat is being absorbed. So as you continue to go right on this heating curve, more heat or more thermal energy is being added into the water, and that's how it is changing states of matter. And so these questions, first, we're going to define a plateau. That's a flat area, just like in geography. And so during the plateau at 0 degrees Celsius, so this part right here, there's a mixture of, so it wants to know what states of matter water would be a mixture of at 0 degrees Celsius. It'd be a mixture of solid and liquid because it's melting right there. And then at 100 degrees Celsius, this plateau, it would be a mixture of a liquid and a gas. And then a pure phase of matter, that means when water is only a solid, only a liquid, only a gas, that occurs at what parts of the heating curve? The diagonals, not the plateaus. Okay. 2. During the heating process, which of the 5 parts of the heating curve experiences a change in temperature? Well, if you did not notice, temperature was the y-axis. And so, what parts of the heating curve is the temperature changing? Well, it's changing right here at this diagonal because the y-axis is going up. Same with here, same with here. Temperature is not changing at the plateaus because it might not actually look like it, but it's supposed to be. It was, okay, not my best word drawing, but those are supposed to be flat lines, which means because temperature is my y-axis, it's not changing right there. The temperature is staying the same. So which parts experience a change in temperature? The diagonals. There is no change in temperature at those plateaus. 3. Kinetic energy. The energy is the energy of particles in motion. Based on the definition of temperature, which you learned yesterday in your Nearpod, it must be true to say that a change in temperature equals a change in the kinetic energy of a system. So during the heating process, which of the heating curve experience a change in kinetic energy. Well, we just said in number 2 that the diagonals get a change of temperature because they are having a change in their y-axis. And so if they're having a change in temperature, then the diagonals are also having a change in kinetic energy. But that would make sense because you learned yesterday that temperature is a measure of the average kinetic energy of a substance. So if the temperature is changing, let's say the temperature is going up, there's now more kinetic energy in that substance. Okay. Number 4, is there a change in kinetic energy during a plateau? No. And why isn't there a change in kinetic energy during a plateau? Because there's not a change in temperature. It is a flat line. So the kinetic energy is staying the same at those plateaus. Okay. Potential energy. You read about this in your notes yesterday. It's the energy of matter based on its position, or stored energy. As the intermolecular distance, which is the distance between molecules, increases, the potential energy increases. So which phase has the greatest amount of potential energy? Well, what state of matter, solid, liquid, gas, is the distance between particles or molecules the greatest? You learned this last unit. Gas. And then solids have the least amount of space in between particles, so they would have the least amount of potential energy. And so when it comes to energy and heating curves, I really need you to get inside your head that temperature is the average kinetic energy. So when temperature goes up, the kinetic energy goes up. The particles move faster. Okay, number 7. The line heat of vaporization is, that should say the line of, or line 4, the heat of vaporization, which was this long one, is much greater than the heat of fusion. So does it require more heat energy to melt or to boil water? Well, if you didn't remember, this x-axis is called heat being added. And so we could see this plateau, the vaporization one, requires a lot more room on the x-axis than the melting one does. So it requires more heat to boil water or to vaporize it because it's a longer plateau. Okay, number 8, heat is being absorbed during a plateau. We know that because that's what the x-axis is. Heat is being added. And so what is heat doing during a plateau since the temperature is not increasing? Well, in your notes yesterday, you had whenever heat is added to a substance, it can do one of two things. It can change into Ke, or it can change into potential energy. Well, we know based off this heating curve that at a plateau, the flat spot, that it is not changing into kinetic energy because the temperature is not changing. That's why it's the flat line. So that means during a plateau that the heat energy, the thermal energy, is changing into potential energy. That is the only option. Number 9, temperature measures. I hope you get this by now. Kinetic energy. So what happens to the kinetic energy as the temperature increases? The kinetic energy would increase. So what happens to the amount of kinetic energy when heat is added to a pure phase of matter? It says A, C, and E. That's A, that's C, that's E. We should have labeled this before. That's okay. And then the plateaus are B and D. That comes into play in that's supposed to be a D. The next question. So back to 11 again. What happens to the amount of kinetic energy? And so when you see kinetic energy, I want you to think, so what happens to the temperature? when heat is added to one of these diagonals, A, C, or E. Well, remember, our x-axis is heat being added. So as I add heat, the temperature is going up. So the kinetic energy is increasing. Number 12, what happens to the kinetic energy or to the temperature when heat is added during a plateau? Nothing. We already said that. At the plateau, there's not a temperature change. And so if heat is constantly being added. We said this earlier. At the plateaus, the flat part, heat is not becoming kinetic energy. So instead, it must be becoming potential energy. And so what parts of the heating curve have a change in potential energy? The plateaus, or B and D. And so those plateaus, that flat part, that is where the phase change is occurring in that flat area. That is where it is actually melting, and it is actually going from solid to liquid, or it's going from liquid to gas at this part. It's like half a liquid, half a gas up here. Right here, it's half a solid, half a liquid. And then once you get to the end of the plateau, it would be completely a gas. And the end of this plateau, it's completely a liquid. But that flat line, it's changing states of matter. And so as that heat gets added and is on that plateau and it's becoming potential energy, it is just separating those particles apart. Because if you remember, we just said that gases have the most potential energy, which means that they are the farthest apart, which is true. And so heat, as it's added at the plateau, changes the state of matter. It separates those molecules because solids are the most close together, liquids not so close, gases far apart. And then the last part, we're going to identify the following phase changes as being endothermic or exothermic. So endothermic requires energy to be added. An exothermic change requires energy to be released. And there's a little trick if you can remember this heating curve. The x-axis of the heating curve is heat, which is energy, being added. And then let's label our states of matter. This is a solid, a liquid, and a gas. So as you go right on the heating curve, heat is being added. And so what does that mean? For A, melting. What is melting? Melting is when it goes from solid to liquid. Well, to go from a solid to a liquid, you have to go from here to here. You have to go right on the heating curve. That's going right. And so that would be energy being required. That would be an endothermic change. Another way I think about it is if you can't think about the heating curve moving right on it, I think about, okay, I know solids. Solids move really slow. Liquids move a little faster. And so to move faster, does it require the solid to gain energy or to lose energy? And hopefully you can think, okay, liquids move faster than solids, so the solid must gain energy. That's why it's an endothermic change. Okay, next one, vaporizing. That is the same thing as like boiling. So going from a liquid to a gas. Liquid here, gas here. That's going right on the heating curve. So that means heat is being added, so it's endothermic. Or if you think about it the other way, liquids, gases. Which one moves faster? Gases move faster. And so for that liquid, for those particles to move faster, they have to absorb energy or get energy added. That's why it's an endothermic change. Condensation. Have you ever woken up in the morning and there's condensation all over your car? Condensation is going from a gas to a liquid. And so if I'm going from a gas to a liquid, I am actually, let me erase all of that. You are going, if you follow my red pen, from a gas to a liquid, left on the heating curve. Or thinking, so that means energy is being released. It's an exothermic change. Another way to think about it, the way I have been for other phase changes, just for me, it makes sense and it's easier to remember. Gases move faster than liquids. So for the gas to become a liquid, it has to slow down. If it's going to slow down, it must release energy. That's why it's an exothermic change. Freezing, D, which I'll just do that one down here. Freezing water is going from a liquid to a solid. So liquid to solid, that's going left on the heating curve. And that's the same thing as condensation. The liquid moves faster than a solid, particles in a solid do. And so to go from the faster moving liquid to the slower moving solid, it has to slow down or release energy. Deposition, that's not a state of matter that, or sorry, not a state of matter that I would expect you to know off the top of your head, but state of matter, sorry, the phase change, deposition, is when it goes directly from a gas to a solid. And so thinking about our heating curve going from gas to solid, you're moving left, so it's exothermic. Also, gases move faster than solids, so to slow down, it has to give off energy. Sublimation, if that's not another phase change, I would expect you to know, and I'm going to have to erase some stuff, that's okay. Sublimation is going from a solid to a gas automatically. If you have ever seen dry ice is solid carbon dioxide, super cold, you could buy it at the store, but I think you have to be 18. And so to go from a solid to a gas, the gas particles obviously move faster, and so it has to absorb energy. So that's an endothermic change. Also, it's going right on the heating curve from solid to gas. And then the last one, fusion. Fusion is another word for melting. And melting is an endothermic change, as we said earlier. And so this is reading a heating curve. Honestly, at the end of the day, what you need to be able to do is, and I'm going to erase this. Looking at this heating curve, I need you to know that this part is a solid, this part is when it's a liquid, this part is when it's a gas, and that these plateaus are phase changes. And then I need you to be able to identify which phase changes are endothermic and which ones are exothermic. And you can either remember it as, if you go from left to right on the heating curve, that is endo. So solid to liquid, liquid to gas, solid to gas, those are all endothermic changes. And then if you go left, those are exothermic changes. So gas to solid, gas to liquid, liquid to solid. Or think about it in terms of the speed of particles. Are the particles speeding up? So they're getting faster, it's an endothermic change. If they're getting slower, it is an exothermic change.